Welcome to your first lecture in Calculus 1. I think a good thing to start with is what is calculus and how can we use calculus in a lot of different areas. So we'll start with basically what are the two big branches of calculus. Well, calculus is divided into differential calculus and integral calculus, and we'll be looking at both differential and integral calculus this semester. However, before we can get started with differential and integral calculus, we need to study the concept of a limit. So differential calculus is working with finding the tangent lines to curves, and that's definitely something that we're going to be starting with very soon. And then a little bit later on in the semester we'll be looking at computing the area underneath the curve. And there are so many other applications to calculus than these two, but these are kind of the general go-to descriptions of what you can do with differential and integral calculus. So to get started, let's go ahead and start with the idea of limits, rates of change, and tangent lines. Okay, when we're talking about limits, rates of change, and we use rates of change so often that we abbreviate it ROC, and tangent lines, we need to start with some basic definitions and ideas to kind of get us all on the same page to understand what we're talking about. So to get started with here, rates of change, and again that's abbreviated ROC, is the relationship between two changing quantities. So some examples here might be velocity. So with velocity, it's the rate of change of position with respect to, and this WRT means with respect to time. So again, I'm talking about the relationship between position and time. Now position is changing and so is time changing as you're driving down the road. So again, the relationship between two changing quantities. A couple of other things that we could talk about here are infection rates of a disease. Could be the flu bug traveling across the United States, so infection rates. Also, we could talk about interest rates. So with interest rates, we're talking about how your money is changing, increasing or decreasing over time. So those are a couple of examples of rates of change. Now there's a couple different ways that we can talk about rates of change. For this first piece right here, we could talk about when we assume rates of change are constant, but that's really actually not very likely. When we talk about driving a car or flying in an airplane, what we're talking about is something going starting at 0 and then coming up to a certain velocity or speed and then slowing back down again. That rate of change is not constant. So let's go ahead and talk about the case where rates of change are not constant. If x and y are related, so something like position and time are related somehow, the rate of change tells us how much y changes in response to a unit change in x. So this would be something like 27 miles per hour. Okay, so how much y changes 27 miles in response to a unit change in x. Unit changes in x would be, let's say, 1 hour in that case. But again, this only applies when rates of change are constant. So let's go ahead and look at a pretty basic short problem that assumes rates of change are constant. So walking through this example, and again we're assuming constant velocity here, but that's really not a valid assumption all the time. But that's the easiest assumption. We know from way back when that distance equals rate times time. This is a formula we've been using in our mathematics careers for a long time. Now if velocity of changing, this formula no longer applies, because if you can see this, the rate is what we're looking at here. Rate is basically related to velocity. And if this is changing, how will this formula work? What if my rate was 2.5 miles per hour and then it switched to 2.8 miles per hour? I couldn't use this formula anymore. So again, this only applies when rate or velocity is constant. If velocity is changing, this formula doesn't work anymore. So if we traveled for 4 hours at 75 miles per hour, distance equals rate times time, what I end up here with is a distance of 75 times 4, or 300 miles. And again, units are always important, so let's include those. So the next problem is, well, what do we do if velocity is not constant? What do we do if velocity is increasing and decreasing? So if velocity increases and decreases, arrow up of course means increases and arrow down means decreases. The answer to that question is we use calculus. So that's one of the nice applications again of calculus that we're going to be able to look at. So if I don't have a constant velocity, if I have changing velocity, I can use calculus to help solve some of those problems. So we're not going to see exactly how to deal with that right now. We're going to kind of back our way into that and be able to solve this question then by the end of the lecture. to start to define this problem, the first thing we need to start looking at are tangent lines. So when we start talking about tangent lines, a good place to begin with is a definition. Now, the standard tangent line definition that I always remember from school was, a line that's tangent to a circle touches the circle in one spot. It can't touch the circle in two spots. Well, we kind of have a different problem with that in this particular sense, because we're not just working with circles, we're working with any shapes. So a better definition for a tangent line is basically a line that skims a curve. In every book will give a little bit different definition, but this is a nice one that works well for what we're working with. So let's go ahead and look at some pictures. There's our nice little circle. This is the one we're working with. And here's a tangent line. And we'll make that dot there so it does look like it skims a curve. And we could also look at a parabola. If we talk about a line that's tangent that skims the curve, we can see that this line is tangent at this point. However, this line up here is not tangent because it definitely doesn't skim the curve. It touches in two spots. We could also look at something like a third-degree polynomial curve or a sine curve, something similar to that. And we could look at a tangent line. Well, we can see that this line skims the curve, so this is a tangent line. But this one only touches in one spot too, but it definitely does not skim the curve. So in terms of tangent lines, this one is a yes, skims the curve. This one is a yes, so is this one, and these two are no's. This one is not tangent because it definitely doesn't skim any curves, and it intersects in 2 points, so that kind of makes us wonder if it's a tangent line. This one intersects the curve exactly once. However, it doesn't skim the curve. It doesn't run right alongside the curve. This one, in fact, looks like it cuts it right in 2 pieces. So these are examples of things that are tangent lines and things that are not tangent lines. And again, we're going with the definition of a line that skims the curve. Now let's go ahead and take this idea and start developing the concept of tangent lines and turning them into the concept of velocity. So let's look at 2 ideas of velocity. The first one that we're going to look at is instantaneous velocity. That means the velocity an object is traveling or going at an exact amount of time. So when we talk about instantaneous velocity, we're talking again the speed and direction of an object at a particular moment. So velocity has 2 things, speed, but also direction, positive or negative here. So keep that in mind when we're talking about velocity at a particular moment. Now, to find the instantaneous velocity, this is really difficult without calculus, but we're going to try and come up with some ideas on how we can develop this without calculus, not using calculus techniques. We're going to see how difficult and kind of long of a process that is, and then we're going to introduce some calculus techniques to help us find that a little bit faster. And then we look at average velocity, and this is the average velocity is the velocity we like to talk about. That's distance equals rate times time. What this is assuming is the rate is constant. Okay. Now if we solve this nice little algebraic equation d equals rt for r, rate, which we can relate back to velocity, rate is equal to distance divided by time. Well, what is distance? How far do we know we've gone? Well, we take how far we went minus how far we started at. So if we talk about traveling across the state of South Dakota, if we started at mile marker 50 and we ended up at mile marker 150, we take 150 minus 50, and we knew we'd travel 100 miles. Same way with time. So what we have here then is a definition that talks about change in position over change in time. Now this triangle is the Greek letter delta, and we use that to represent change. So change in position over change in time. Now so there's some other syntaxes that we're going to want to make sure that we're aware of as well when we're working these types of problems. So to get started, let's go ahead and define a few things. This is the letter S with a P hanging from it. This means suppose, and you'll see these a lot in our notes. So again, the letter S, this turns it into a P, so this means suppose. Now some of these will be familiar to you if you've ever had a physics course. S naught is our initial position. Okay, S1 would be our position at time 1. Okay, and then we also have T naught and T1. T naught is our initial time, and T1 is our time at time 1. And I say time at time 1 because that would be like the first observation that we took our, see how far we've been traveling or how long we've been traveling. So for our example, I want to say our initial position is 0. We start at 0, so perhaps the origin. Then I want to look at my position at a particular time 1. Well, I'm going to say time 1 is 5 hours. Okay, and for here, then at time 1, I can see that I've been traveling for 5 hours. My position at time 1 then would be 150 miles. Now my initial time is 0, kind of like starting the stopwatch at 0. So from this information I can find my average velocity. And we're putting a lot of work into a very easy problem, but again we're going to add some layers of complexity to this very soon. So average velocity is our change in position over our change in time. And again, that came from this formula right up here, change in position over change in time. Well, change in position is S1 minus S naught over T1 minus T naught. And again, this formula is going to be important. 150 minus 0 minus, or sorry, divided by 5 minus 0. 150 over 5, and I get 30 miles for my units in the numerator. In my denominator, I get over 1 hour. So I basically traveled 30 miles in 1 hour. Kind of a slow trip. Now, however, after saying this, at any given moment the car may be going faster or slower. This is only the average speed. So we know when we started out we were going 0 miles per hour. So this doesn't represent that start time, and maybe sometime along this trip we may have been going 80 miles per hour and then slowed way back down again. So again, this is what we're only talking about here is the average velocity. Now, why can't we find an instantaneous velocity using this formula? Well, we cannot find instantaneous velocity with this formula because in order to use instantaneous velocity, my initial and my time 1, or my final time, would have to be the same. And basically what would that mean then? T1 minus T naught, the difference would be 0, and I'd have the change in position, which is some value, over the change in time would be 0, and we know that dividing by 0 is undefined. So we cannot find instantaneous velocity using this formula. However, having said that, we should be able to get a really good estimate of instantaneous velocity by using a very small time interval to compute the average velocity. So what we could do is, instead of taking a time interval of 5 hours like we did up here, maybe we could do a time interval of, let's say, a couple seconds. So average velocity, change in distance over the change in time, over a very small time interval will give me an idea of instantaneous velocity. So when we start talking about velocity or instantaneous velocity, we kind of have to wonder, where do these functions come from? Well, if we're talking about average velocity, we're assuming constant speed, and basically constant speed would be a linear function. Well, what if it's not a linear function? For instance, if you released an object at some time equals 0, the distance traveled after t seconds is given by this formula right here. Well, what does this thing look like? If we were to graph this function, again, s of t is position at time t equals 16t squared, this is a parabola. Okay, and it's a parabola going through the origin, so it looks something like this. And so again, what we're talking about here is throwing an object from at rest at t equals 0, it's not moving very fast, and then what we have here is then the distance traveled. And the further the time goes out, the further the object travels, and that makes sense. But this is just one of very many functions that we can be used to determine velocity and instantaneous velocity. And this one is basically Galileo's idea of when we were talking about seconds. Here we're not talking about miles per hour, we're talking about time in seconds. So let's go ahead and look at an example of a problem where we're trying to talk about an average rate of change, not velocity, but an average rate of change which we can turn into velocity eventually. And this example is going to be involving money. So let's look through this. With initial deposit of $100, the balance in a bank account after t years is given by this function. So the function is provided for us in this particular case. So the function is f of t is equal to 100. 100 is what's representing our initial deposit. 1.08, that's an interesting question. That's going to be something that we figure out means something to do with interest, but we'll answer that eventually. And t is the amount of time in years that this is invested. So there's a couple of questions that we can ask here. First of all, what are the units of the rate of change of f of t? When we talk about our units, we're talking about the change in y over the change in x, the change in position over the change in time. Well, this is change in money over the change in time. So our proper units here would be dollars per year. So those are our proper units. Now the next question is I want to find the average rate of change. And again, ROC stands for rate of change. Find the average rate of change over two different intervals. I want to see how fast that money is growing between 0 and 0.5, so beginning from my initial deposit to half a year. And I want to see that rate of change between 0, my initial deposit time, and 1 year. So two different things going on here. So the first thing I want to do, I want to find the average rate of change between 0 and a half year. Now when you're working through these problems in your notes, it's a good idea to hit pause, grab a calculator, and actually crunch these numbers yourself to make sure that they're correct, first of all, because mistakes do happen, and then also it gives you practice understanding the concepts. You don't want to just copy down my notes. You want to produce these problems on your own. So to get started here, the average rate of change between 0 years, or my initial deposit time of 0 and a half year, would be the change in position over the change in time. Well, my change in position is given by f of t, this function right up here, and I always take my right endpoint minus my left. That's the same way if I went from 50-mile marker to 150-mile marker. If I wanted to figure out how far I'd travel, I'd go 150 minus 50. So I go f of 0.5 minus f of 0 divided by 0.5 minus 0, change in position over change in time. Now when I plug these into my original function and chug these numbers through my calculator, I get my average rate of change is $7.84, or about 85 cents per year if we rounded it up. Now we don't want to over round here, because a lot of times when you end up over rounding, you end up with some errors, just because we're talking about money here, and because our rates of change are going to be so small sometimes, we want to carry it out a little bit further. Now the next thing we want to do is part 2 of this problem. We want to find the average rate of change between 0 and 1 years. So we run through the same thing again. The average rate of change between 0 and 1 years is f of 1 minus f of 0 over 1 minus 0. The change in position in my account over the change in time. So I plug these into this original function that was given to me up here. And I end up with $8 per year. That kind of makes me think about something. I invested $100. At the end of 1 year I had $108, including my interest. Maybe that $8 per year and $100 interest is implying that I have an interest rate of 8%. So this kind of comes and helps us figure out something like an interest rate, okay, dollars per year earned. So this is an example where we're using the idea of rates of change not for speed, velocity, etc., but trying to determine an interest rate, the growth of a savings account on a particular function. Well, I want to continue on with the same example. So same example, we're going to be looking at part C here. I would like to estimate the instantaneous rate of change at t equals 0.5 years. So I don't want to know what's going on between 0 and 0.5. I want to know what's going on at exactly 0.5 years. Now the idea behind this is how we're going to do this is we are going to find a very small interval. So instead of going 0 to 0.5 as my interval, I might go 0.4 to 0.5 and 0.5 to 0.6. So I'm going to find the average rate of change somewhere to the left and somewhere to the right, and then I'm going to make that interval smaller and smaller, and then what I'll do when I make that interval smaller and smaller, that will converge or go toward the actual instantaneous rate of change, even though I know I can't find that, because remember, you can't divide by 0. So again, to get started here, you want to hit pause. You probably want to fill out this table, but not the numbers in it. I want you to calculate the numbers because that's going to help solidify in your mind exactly how this process takes place. So to get started here, I'm trying to find the instantaneous rate of change at 0.5 years. And I can't do that because when I have my denominator, 0.5 minus 0.5 would be 0. So what we're going to do is we're going to find what's going on with intervals to the left and to the right of 0.5. So to get started, I might look at a small interval 0.49 to 0.5, and I'd look at my change in my position over the change in time. And this is an example, again, we've done these up above, but how I would do that. I'd run through this process, change in position over change in time, I'd go through and calculate that, and the average rate of change between 0.49 years and 0.5 years here is about $7.99.5. So looking at this, I can see that here, this is a division here, I can see that I'm getting closer and closer. After I do this repetitively from the left, I'm approaching $8. Now from the right, I'm looking at intervals that are slightly larger than 0.5. So I'm going 0.5 to 0.51, 0.5 to 0.501, etc. And I'm doing the same thing over and over again for all of these. I'm looking at the change in position over the change in time. Now from the left, you can see that I'm getting closer and closer to $8. From the right, you can see I'm getting closer and closer to $8. So my estimate, the instantaneous rate of change then at 0.5 years is $8 per year again. So again, limit from the left, limit from the right. And I'm using this idea of a limit to say I'm approaching it. I'm getting closer and closer to a particular value. This is a lot of work, and you're going to be doing these in class. So please don't just scribble down all these numbers for your notes. Actually go through, crunch these through, write a spreadsheet. Excel does a wonderful job once you get your function defined to actually make these tables. So again, take a minute, go through and actually recreate these numbers. Don't depend that they're correct. I could have a mistake in my lecture, and if you find one, let me know. But again, don't just copy them down. Work through the problem. So again, what can we conclude from this? Well, again, I estimated that the instantaneous rate of change at 1/2 year was $8 per year, which relates to an 8% interest rate. And remember that f of t formula that we were given used 1.08 here, so that 0.08 is my interest rate. Now, what if I had 10%? I think this would be 1.10 if I invested $100, and t is the number of years again. So this kind of gives me an idea. The average rate of change, which we just got done calculating up here from the left and the from right, approaches, that's what this arrow means, is approaches or goes toward the instantaneous velocity. Well, that's a huge idea. So rates of change over very, very small intervals, if I look at their behavior from the right and to the left of a particular point, approach or go toward instantaneous velocity. This is huge. We're really going to be able to use this idea, and the way we're going to start this idea off is we're going to look at a graphical approach to this. So with our graphical approach, let's go ahead and look at instantaneous rate of change. So we're going to be able to look at instantaneous rate of change and velocity in this graphical approach. So again, instantaneous rate of change, rates of change, ROC means rates of change, and velocity are related. So let's go ahead and get started looking at this. So first of all, if I have this curve right here in black, and it's just some curve, we don't need to have a function that defines it, I could look at, see what's going on if I thought about traveling or moving across this curve over a certain amount of time. Now remember, t0 is my initial time, t1 is my final time in this particular case. Now at t0, what this is saying is I'm at this particular position. So s of t0 means my position at t0. That's this point right here. Now at t1, we can see on this curve I'm over here at position s of t1. So this is this point. Now, because I'm not skimming the curve and I'm crossing in two spots, what I can call this is a secant line. So a secant line has a particular slope. A slope of any line is the change in the y over the change in the x, but in this case the y variable is my position variable. It's my vertical variable here, so this is change in position over change in time. This is also defined as my average velocity, so that's interesting. So I can basically interpret velocity as slope. Average velocity and slope are directly related, as we can see in this graphic. Now let's go ahead and take that idea a little bit further. So what we're going to do is we are going to look at that nice function that Galileo gave us, and we're going to look at the function 16t squared. So that's my position at time t. And we're going to estimate the slope of the tangent line at t equals 0.5 seconds. This is difficult to do because, again, that's a change in y over the change in x. So I need some right and left endpoint for that denominator. I need the slope over two numbers here, between two numbers. That's how I can find slope. In order to find the slope of a line, you need 2 points. I can't find the slope of the line at one point without using ideas of calculus, which we're trying to develop here. So I think the first thing that we should do is probably do a quick little curve sketch of this function. Okay, this is pulling an awful lot in one spot, and I apologize for that, but my stylus isn't working very good, so I don't want to have to continually stop the recording and rewrite. So let's go ahead and look at what we have here. So 16t squared. So here's my Cartesian coordinate system. I'm only looking at the first quadrant here. 16t squared is this black line. This is the parabola opening up, but I'm only looking at the right hand side of the parabola because the left hand side of the parabola would be negative time. So at 16t squared, I'm trying to figure out what's going on at exactly 0.5 with the slope. And so what I do is I start with and I find the slope at all sorts of different positions using this point and let's say another point up here. So here, if I use this particular line, I'm going to look at the interval between 0.5 and 0.6, change in y over the change in x. And again, distance traveled here is pretty easy to find when I'm looking at plugging in 0.6 into here. 0.6 squared times 16 would give me this height. And so what I want to do is to find the slopes of all of these lines, and I will show you how we do that first one. So this first one, I come down here and I try and find the slope between 0.5 and 0.6 seconds, time in seconds here. Change in position over change in time. S of 0.6 minus S of 0.5 divided by the difference in those times. And I get 17.6 here. So my slope is 17.6 and that's given in red. Now I'm going to do the same thing right here for the interval between 0.5 and 0.55, and that will be this blue line. So let's go ahead and run through those calculations as well. So here's how I'd calculate the slope of the line between time of 0.5 and 0.55. Same exact problem, same exact approach, and I would get these values for my slope. Now a couple things I want you to do is don't just copy this down. Go ahead, do these problems yourself. Find these slopes yourself. You can do this. And make sure you can verify my numbers. So again, 17.6, 16.8, 16.16. So 17.6, 16.8, and 16.16 we have right here. And so what's happening is I'm getting closer and closer and closer, as you see, to the true slope. So I think the one that's the best estimate of the slope is not 17.6, but probably closer down here to 16.16. So let's go ahead and look at that trend. So we can see here that the slopes of the secant lines are approaching the slope of the tangent line at t equal 1/2. Now from calculus, what we can get out of this is the actual tangent line slope is 16. So we can see we're getting pretty dang close here. We could even go a little bit closer, like maybe 0.505 or 0.5005. But you can see also that there's a lot of computational work that goes into this. So again, a spreadsheet is a nice little thing to work with here. You can also work with Maple, but I kind of like a spreadsheet for this, just because I like working with spreadsheets. But again, the big idea here is right here. From calculus, the actual tangent line is 16, and we got pretty close. And we could get even closer if we had closer intervals. And so that's the big idea. That's what we kind of want to keep in mind here, is that the average velocity over smaller and smaller intervals approaches the instantaneous velocity. And the way this works is by taking this time interval, and we want the time interval to get closer and closer to 0. So basically in the horizontal axis up here, we want this region between 0.5 and 0.55, we want to squeeze this down and get closer and closer and closer. And the closer we can get, I can't actually equal 0.5, but I can get really close, I will actually find that instantaneous velocity. So it's the time interval difference gets closer and closer to 0. And another way we could write this is delta t. gets closer and closer to zero, the average velocity approaches the instantaneous velocity. And this is the big takeaway. This is the huge idea that we want to get out of this lecture. And again, I can't stress to you the importance of you working these problems through that I have here in the lecture by yourself, so you see the process, so you can match my solutions. Don't just write it all down. Actually work through them, because when you do them in class and when you do them for your homework, then you'll kind of have a frame of reference to go after that, because you've worked one full problem by yourself and matched solutions. So good luck working these problems. They're really interesting, and pretty soon we'll get to an easier way to approach the same idea, but I think it's really important to have those underpinnings of why that will work eventually. Good luck.